This is the third video for application of forces, and in this video we're going to look at problems with static rigid bodies. Now remember, static means it's still. A rigid body is something like a beam or a ladder. So we're going to have a little look at these questions, these next two. So sometimes we need to consider rotational forces acting on the rigid body, and this is where our work on moments comes in. So for a rigid body to be in static equilibrium, first of all, the body must be stationary, i.e. the static. The resultant forces must be zero, and the resultant moment must be zero. So we're going to have a little look at this question. So in this question, this is question 7 in your booklet. It says a uniform rod. So I'm going to underline key things. So first of all, uniform, which means that the centre of mass is going to put it at the halfway along the rod. A uniform rod AB of mass 40 kilograms and the length 10 rests with end A on rough horizontal ground. Okay. The rod then rests against a smooth peg. Now, you all know what a peg is. It's something that's sticking out of the wall, and it's literally just leaning on it. But the important thing about this one is it's smooth. And the length A to C is 8. The rod is in limiting equilibrium at an angle of, so limiting equilibrium, quite important. All right, it's just about to slip an angle of 15 degrees to the horizontal. So the first thing we need to do is we need to draw a really good diagram. So I'm going to start my diagram here. So I have that's the ground. Okay. Here's the rod, again at 15 degrees. Here is 15 degrees. It's leaning on a peg that's sticking out of the wall, and that's C. Okay, and that's what we've got. That's the system. Now we're going to put all our forces on. So I'm going to do those in red. So at the end of the ladder, at the end of the rod, that's resting on the ground, so we're going to have normal reaction. So I'll call that RA. Okay, and the other force that we've got at A is friction. Now, if this thing is going to slip, it's going to slip, the rod will slip to the left, and therefore friction must be acting to the right. Okay, now we've also got the weight of the rod, and as we were told it was uniform, that is acting here, halfway along. Okay, yeah, I'll call that mg, so that's 40 g, 40 times gravity, and that's acting, I'll put a little measurement on, 5 meters. Okay. Now there is one more force. Okay, so the rod is pressing on the peg, so the peg is pressing back on the rod. Because it's a circular peg, we're going to have a normal reaction here, but we'll call that RC, and that is acting perpendicular to the rod. So we've got all our forces on. Okay. Now, what we're going to do in order to find the magnitude of the reaction at C is we're going to take moments. Now you can see we're going to take moments around A. So we're going to take moments. So I'm going to tell the examiner, take moms at A. That means that RA and friction have no turning effect, none at all. Okay, so I've only got two forces that are attempting to turn this system, and of course they're matching each other simply because it's in equilibrium. So I'm first of all going to deal with the weight, the 40g. Okay, so that will be trying to turn the system clockwise. So the weight is 40g, and the perpendicular distance of the line of action of that force to the turning point, which of course is at A, I'm going to show in the little blue line. That blue line, that little blue line there is the perpendicular distance of the line of action to the force. Okay, and you can see that that is the adjacent to the 15, so it will be times by 5 cos 15. Okay, now notice that RC is acting perpendicular, so therefore that will try to turn us anti-clockwise, so that will be RC times by, well, we know that the distance A to C is 8, and you can see from that the only thing that we don't know is RC, and if you type all that into your calculator, okay, you will get that RC comes out as 236.65, which of course we're going to cut to either 2 or 3 significant figures, so that will be 237 newtons, that's 3 significant figures, or another option, because we've used G, is 240 newtons, and again that's 2 significant figures. Now the next thing we need to do is we need to find the coefficient of friction between the rod and the ground. Okay, and in order to do that, I'm going to resolve my forces. Now remember that coefficient of friction, okay, is a measure of roughness between the bottom of the beam, the rod, and the ground. So we know that friction equals mu RA. Okay, that's quite important to us. Okay, because it's in limiting equilibrium. If it was not on the point of moving, friction will be less than mu RA. Okay, so we're going to do some balancing of forces. Now, you can see we've got 4 forces on my diagram. I'm just going to go back to it, and 3 of them are vertical or horizontal. There's 2 vertical and there's 1 horizontal force. Now what I'm going to do is I'm going to resolve the RC. I'm going to resolve the normal reaction. Okay, so I'm going to take it up and across like that so I can see. And of course this angle here is also 15 degrees. Okay, it's very similar to when we resolve weight. Okay, so we've got this one. This is RC cos 15, and this one is RC sine 15. Okay, you can come left and up. I just decided to go up and left. Okay, so we're going to do some balancing of forces. Now I'm going to have to keep going back to the diagram. Okay, so the first thing we're going to do is we're going to say up equals down. So you can see from my diagram that you've got 2 forces going straight up and you've got 1 going down. So I'm just going to write those down. Okay, so you've got RA plus RC cos 15 equals 40G. Okay, now we want RA, so therefore RA equals 40G minus RC cos 15. And of course we found RC in the last part, in part A, so I'm just going to put that in. So that tells me if I put my value for RC in, and I'm going to use a more accurate answer than the 2 or 3 significant figures, but it comes out as 163.41 newtons, and I've just done it there to 2 decimal places or 5 significant figures. We then need to do left equals right, because remember I need friction. I've now got RA, so left equals right, and again if you look at the diagram, the force that's going left is RC sine 15, the force that's going right is friction, so therefore friction equals RC sine 15. Okay, put in the RC value from part A, so friction comes out as 61.25 newtons. Okay, I'm just popping that in. Okay, and we know we want the value of mu, the coefficient of friction. Mu equals friction divided by RA in this case. So therefore, mu equals 61.25 over 163.41, and our mu value comes out as 0.37 to two significant figures. Now, if I was going to use that in another part of the question, I'll probably write it to a little bit more accuracy so I can use it, but that's the answer to this one. Okay, so we're now going to have a little look at a ladder question. Very, very similar. Okay, so we've got the diagram here. So it says a ladder AB, I'm going to do some underlining, ladder AB of mass M and length 3A has one end A resting on rough horizontal ground. Okay, the other end B rests against a smooth vertical wall. That means there's no friction on the wall, there's just friction on the floor. A load of mass 2m is fixed on the ladder at point C, where AC is 8. The ladder is modelled as a uniform rod in a vertical plane perpendicular to the wall, and the load is modelled as a particle. And remember what those modelling assumptions are. The ladder rests in limiting equilibrium, so it's about to slip at an angle 60 degrees with the ground. So we need to first of all find the coefficient of friction, which is the long bit. So the first thing I'm going to do, as we always should do, is put on all our forces. So I'm going to put my forces on, I'm going to put them on in green. So the foot of the ladder got RA, and if this ladder is going to slip, it's going to slip to the left, so friction must be acting to the right. We've also got a reaction at B, so that's RB. Okay, we've got the weight of the ladder, and that's going to act 1.5A or 3/2A. So I'm going to put that there. Okay, and that is mg. We don't know what the mass of the ladder is, so all I can say is it's mg. And we've also got the mass at C, which is 2 mg. Okay, so I've now got all my forces on. I'm just going to write a few little measurements. Okay, so you can see from A to the middle of the ladder, that is 3/2A. Okay, A to C is A, and of course the whole ladder is 3A. Right, so there are two things we're going to need to do in this question. We're going to have to balance our forces, so up equals down, left equals right. We're going to take moments, and we're going to use friction equals mu RA because it's about to move. So let's just jot a few things down. So the first thing I'm going to do is I'm going to do up equals down. So up equals down, you can see therefore RA must equal 3 mg. And I'm going to leave m and g in this question. Okay. Right, I'm going to do left equals right. I'm going to do it on the same line. Left equals right. So left equals right. Therefore, friction equals RB. But if you remember, it's just about to slip. So friction equals mu RA. So therefore, RB equals, because I know the friction is RB, equals mu times 3 mg. Okay. Now, if I can find out what RB is, I can find out what mu is. So in order to find out what RB is, I'm going to take moments around A. So I'm going to do moms at A. Now, in order to do moments at A, remember RA and friction will disappear. Well, they don't disappear, they just have no turning effect. So there are three forces. The two weight forces are trying to pull the system clockwise, and RB is trying to pull the system anti-clockwise. Now, I'm going to start with the clockwise moments. So clockwise. So we've got, first of all, 2 mg. That's the mass that's on at C, okay, and its perpendicular distance to the turning point, the line of action, will be, okay, A times cos 60. I'll just indicate that. Can you see it's this distance here that I've just shown in red? So that's a little right angle triangle. The hypotenuse is A, and that side I want is cos 60. Okay. We've also got the weight of the ladder. So that's mg multiplied by, and again, this time I want this distance. You can see there I've shown in blue, and that is going to be 3/2a cos 60. So that's 3/2a cos 60. Now, the force that's trying to pull the system anti-clockwise, so it will equal the anti-clockwise one, is RB. Now, its line, and I'll show you that one in black, right, is here. Now, that's the perpendicular distance. Now, you'll notice that's the same as the distance up the wall. Okay, I can move it. Right, I can move that. You can see if I move that. Oh, fortunately, it's not letting me move it, but you can see that that will be, therefore, 3a sine 60. Now, if you look at that, you can see the first thing, we've got a in everything, so we can just sort all that out. So I'm just going to, again, sort all that out. Okay. So you've got a in everything, so I'm just going to cancel out a. Okay. And then if you work out your cos 60s and your sine 60s, so you can see on the clockwise moments, you've got 2 mg cos 60 plus 1.5 mg cos 60. Okay, so that's 5/2 cos 60. Okay, and then if you work out what your cos 60 is, okay, so you end up with, when you simplify this, as 7/4 mga equals 3√3/2. So I'll put an a in it, and I should have, apologies. Just get rid of that. Okay, and it's 3√3/2 RB. Okay, now if you rearrange that to get RB, you get that RB is 7√3/18 mg. Now, notice we can now put that back in this top one. Okay, so you end up with 7√3/18 mg equals mu times 3 mg. Notice you've got mg in both, so therefore those now cancel, and divide by 3, and you get your coefficient of friction, or mu, is 7√3 over 54. If you put that in your calculator, you get 0.22, and that's to two significant figures. Okay, so you can see a lot of this is getting very samey. Now the last part of this is state how you've used the assumption that the ladder is uniform. So the weight of the ladder acts at the midpoint. Okay, remember if it was a non-uniform rod, then it wouldn't act at the midpoint. And that's the end of the third video.